Alright, the last thing we need to talk about before we can fully get into a roller coaster project is power. Alright, and power is going to help us calculate the power needed to run a roller coaster. So before I get into this, let's talk hypothetically about this situation. You walk up a flight of stairs, you run up a flight of stairs. Alright, my first question to you is which is more work? So go ahead and think about that for a second, make a choice. Then second question is which makes you more tired? Alright, so I'm not going to give away the answer on this one yet, but I'm assuming we're all going to say that running makes you more tired. Okay, so let's talk about this. So, again, running probably makes you more tired, but is it because you're doing more work? So let's think about the two situations and how they're related. What vertical force is required to get you upstairs? Like what force do you have to overcome? Hopefully you were saying your weight, or mg. Alright? Same force you have to overcome if you run up the stairs. You just overcome the force faster. Okay? What's the distance you have to travel to get up to the top of the flight of stairs? Mind you, this is the same flight of stairs. Okay? So to get to the top, the distance is the height. Alright? But again, same flight of stairs, same person. So far there's no changes. So walking up a flight of stairs, is that going to take more or less time? So that's going to take more time. Whereas running up the flight of stairs is going to take less time. So the question is, are we doing more work? So let's look at our equation. Work is equal to force times distance. So our forces, if you look at the two boxes, they're the same. So no change there. If you look at the distances, they're the same. No change there. Since it's the only thing in our equation, is there a change in work? No, there is not. Okay? What does change is the time it takes to do the work. Okay? And what that's called is power. Alright? So power is the rate at which work is done. Or in other words, how fast is it done? Alright? So to calculate power, all you have to do is take your work and divide it by the time it takes to do it. Alright? Now, the equations can look like, if you know the total work done, you can just take work and divide by time. Alright? But sometimes you might be given the force and the distance, which means you'll have to calculate work as well as divide by time. So you could also see the equation written like this. But both of these will help you determine how much power is needed in order to get that work done. Okay? So the units for power, again, if we look at our variables and derive the units from there, force times distance is going to give us the Newton meter, and then divided by time gives us per second. So they are, you can write it as Newton meters per second, or you can also replace the Newton meter with a joule, so it's also joules per second. But all of this can be abbreviated as one single thing, a watt, which you can abbreviate with a capital W. Okay? This conversion we will use just as an interesting little piece of information with the staircase lab that we do, but horsepowers. So if you think about any car commercial that you've seen where they talk about how many horsepower the car has, especially a sports car, all right? 1 horsepower is equal to 750 watts. So we're actually going to calculate how many horsepower it takes you to go up a flight of stairs. We'll see if you're anything like a car. But let's just do a couple of power sample problems to get your feet wet with these. So how much power is needed to move an object with a force of 100 newtons across a 4-meter table in 5 seconds? So list your knowns. We know that force 100 newtons. We know that distance is 4 meters. We know that time is 5 seconds. And what we want to know is power. Okay? So to choose your equation, we have our two power equations. We have power equals work over time, and we have power equals force times distance divided by time. Which one better fits our knowns? Okay, since we have force and distance, we're going to be using that version of the equation. Okay? So power is going to be equal to 100 times 4 over 5. Or 400 divided by 5, which gives you 80. And what was that new unit we just learned? Watts. Or W. Okay? Or even Newton meters per second. Whatever your preference is, none of those would be incorrect. So one more sample problem. If 50 joules of work is done in 5 seconds, how much power is used? So let's list our knowns and unknowns. We know that work is equal to 50 joules. We know that time is 5 seconds. And our question is power. Alright, so looking at our two power equations, we have power equals work divided by time, and we have power equals FD divided by time. Which one best matches our knowns? So since we know work and time, that's going to be the first one, and not the second one. Alright, so if we substitute, we're going to have 50 divided by 5. Sorry about the extra P equals there, but that's going to give us 10, and our units are watts with a W, or if you really want to, Newton meters per second. Okay? Make sure you have some notes for class and do the online form, and I will see you in class.